Alright, so in this video we are going to do a comparison between the von Neumann architecture, von Neumann and Harvard microcontroller architecture. Alright, in this video we are going to do a comparison. We're going to compare von Neumann and Harvard microcontroller architecture. We're going to start from here. Von Neumann microcontroller, really? Now, that sounds like that because look at this table of comparison. Of course, this side you have von Neumann. This side you have von Neumann. This side you have Harvard. Now, Harvard, it's mainly used for what? Microcontrollers. You see, ESP32. Oh boy, Arduino ESP32. You see, Arduino ESP32, PIC microcontrollers. All these guys work with the Harvard architecture. So when we say, oh, I think I should mention this first. When we say architecture, we mean how the component is built, how they are wired, how they are connected internally. Okay, their bus system, their processing, the configuration for that's the physical hardware configuration, just like architecture, building. Okay, just bear that in mind, hardware, connection, configuration, and things like that. So that's for Harvard. It works. It's mainly used for microcontrollers. For von Neumann, it's mainly used for what? Desktop computers, laptop, and things like that. Now, let's come back to the first one. Memory structure. For von Neumann, it uses a single memory for both data and instruction. One memory is used for data and for instruction. This guy, Harvard architecture, uses what? Separate memory for data and what? Instruction. I think this is kind of the main difference between von Neumann and Harvard. This separation between memory and data. This separation between what? Memory and data. If you hold this one in your mind, you will be able to get out the other parts, the other comparison. Now look at it. Single memory for both data and instruction, right? That is the data you are working on, the instruction, how the data will be used. So data, what you are working on. Instruction, how we are working on what you are working on. Okay? Well, both of them are saved in the same memory for von. For Harvard, they are separate. Now, that's in terms of memory. In terms of bus, they use what? Single bus for data and instruction. They are saying the single again. Very single. Okay? They are saying the single here again. Then for Harvard, they use what? Separate buses for data, separate bus for instruction. Data and instruction are the two things you are looking at here. Von Neumann, single man. Harvard, they are separate. Okay, they are separate. Now, why am I laughing? If you know why, put it in the comment section. Okay. Therefore, speed. Von Neumann is slower because instructions and data access cannot occur simultaneously, because we are using one bus, same bus for data and instruction. When data is going, instruction will wait. When instruction is going, data will wait. So they cannot happen simultaneously. So it is what? Slower. For Harvard, it is faster because instruction can be going to a particular location or can be in execution, and data can also be accessed, okay, because they are in different buses, so they can happen simultaneously. Exactly. Now, because of this, using the same bus, using the same memory, the design is what? Simple. Are we seeing that we are building from the same idea of bus? We are building from the same idea of data and instruction, whether they are together or separate, whether they are single or separate. So because they are single, the design is what? Simple. For this one, because they are separate, the design is what? Complex. Instead of arranging one set of bus, you arrange different set of buses. So it's of course complex. Instead of having one memory, you have different memory. Now, because it is simple, it is what? Less expensive. That's for the von. Because it is complex, it's now what? Expensive. Because it is complex, it is what? Expensive. Whoa. Because it's complex, it's expensive. Why is it complex? We are using different memory and different memory and different bus for data and instruction. The same thing applies this way. It's expensive. It is less expensive because it is simple to design. Simple to design because it's what uses same single memory and bus for data and instruction. So I think we can even stop here. Sef. We can even stop here. But let's just add the rest part. So one operation at a time. Of course, that's obvious. Either you are sending data or you are sending instruction. Okay. For this one, multiple operations can occur simultaneously. Okay. Then, because of this one operation at a time, the performance is low performance. Multiple operation at a time, higher performance. Sequential access, because you have everything going in one line. Data going, the other one will, instruction will wait. Instruction going, data will wait. So it's sequential, one after the other. Then for parallel, then for Harvard is parallel. One instruction is going, data is going side by side, parallel. So now back to von Neumann. Because von Neumann is sequential, it is what less efficient. Of course, this one sounds like we are repeating lower power. So higher power, of course, more efficient. Then used in general purpose computers like desktop computers, laptop. Then this one is used in microcontrollers and embedded system like Arduino, ESP, and PIC, all these things like that. That's it. Okay. So I hope you get it. Thanks for watching, and I'll see you in the next video.